Math. All right, let's see what we're cooking up today in our math lab. We got radium-226. Woo-wee, radium-226. That's a good type of radium, right? That's high-quality radium. It loses its mass at a rate that is directly proportional to its mass. Y'all recognize that wording? Its mass is decreasing, essentially, at a rate that is directly proportional to its current mass. So the more mass it has, the more mass it loses. The less mass it has, the less mass it loses. Okay? So that is going to then follow the rule of what type of growth, or in this case, decay, we could say. Exponential. Yeah, and it's in the exponential section. So yeah, it's going to be exponential. So you can go straight to y equals c e to the kt if you want. Okay? All right, so its half-life is 1,590 years. So it's an unstable isotope of radium. I don't know if there are any stable radium isotopes, but this one has a half-life of 1,590 years, which means every 1,590 years, the element or the representative element that we have here loses 1/2 of its mass. And of course, over time, half, it's going to be losing less and less, but still the same percentage. Will it ever equal 0? No. Okay? And this is kind of why how carbon-14 dating works. Carbon-14 is decay similarly, but a little bit more like 5,000 something years. But there's always going to be a little trace element because it's never going to equal 0. And it's just a matter of, do we have instruments that are accurate enough to measure the trace amounts? So this would be exponential decay because the function is going to be decreasing. We start with a sample that has a mass of 100 milligrams. So if you want to create the initial condition, they're using m of t. So we could say that we have ordered pairs time and mass. Time is our independent variable, mass is our dependent variable. So initially at time 0, we have 100 milligrams of radium-226. And we can generate ordered pairs, can't we, based upon the rule that we have for its half-life? So let's see, 1,590 years later, how much are we going to have? 50, so on and so forth. Another 1,590 would be 3,180. We're going to have what? 25. And we can keep going if we want. 25 to 12, and a half. But I don't think we need to. What is it asking us? Find the formula for the mass that remains after t years. Now, again, you have two options here. It didn't ask us to find K. So you're welcome to jump in and use the sect equation. And for the sect equation, you need to be able to find C and K, which means you need how many unknowns? Or how many ordered pairs? 2, right? And we have 2. So let's do that first. Notice we generated the y-intercept of 0, 100. So, of course, we know then that our value of C could be what? 100. So that takes care of one of the 2 variables. The other ordered pair we could generate, we can use that, 1,590, 50. So we can plug that in, and we got 50 equals 100 e to the 1,590 times k. And like we did yesterday, I can go ahead and solve for k using the second ordered pair that I generated. So 50 divided by 100 is a half, surprise, surprise, e to the 1,590k. And notice that is irrespective of the mass. If your mass were 50 to start with, half of it's 25, this number is always going to be a half. And if you take the natural log of both sides, you get the natural log of a half equals 1,590k. And you solve for k, and you get 1 over 1,590 times the natural log of a half. And as I think Mr. Burquest, I won't say his first name, but it's not San Antonio. Okay, that gives someone who wants to find out maybe a clue. Mr. Burquest said, hey, is it always the pattern that it's going to be the natural log of the, what did you say? How did you say it? I don't know. The reciprocal of the time period times the natural log of the factor. Yeah, the factor at which it grows. In this case, half, right? So this, again, is no exception. So if you needed to find the k value, Thank you. If you needed to find the K value, Thomas, this is for you. If you remember that rule, you can go straight to it. Of course, you can derive it this way. And once you have our K, or we have our K, we can plug it in up here. And we end up with y equals 100 e to the K, which is this wonderful, fantastic thing, 1590 natural log of a half times t. Boy, isn't that pretty? That would be your working model. I may change it from y, though, to what they asked me to do, m of t. So that's speaking specifically towards the problem. All right, so there it is. That would earn full credit if this were a free response. Now, what if that's not an answer choice? Is there another way that we can create this problem, this equation? Because it didn't ask us to find K, you do not have to use the sect equation. You can go straight to what we learned in pre-cal. What was the initial amount? 100. And then you could say, if we're talking about a half-life, the half-life is your base. It's your factor. And then you would raise it to the what? If the half-life is 1590, then you want to make sure that there's another factor of 1/2 every multiple of 1590. So you would have to take t and divide it by the time period. That is also equivalent. That one's a little bit easier to create, okay? And it's also a little bit easier to use, right? If you had to, like, answer a question. Now, the only bad thing about this one, again, is if they're asking you to find the value of K, and if they did ask you to find the value of K, they would say that dm dt equals K times m. They would give that to you, which they could have, but they didn't. That's when you would have to find K, and so that's when you need to come up with this. So let's see if they are, in fact, equivalent. We built it up yesterday from the bottom one to the top one. Let's just very quickly look at our rules of logs and see if they are not, in fact, equivalent. So if I take the one above and manipulate it, I could put this into the t, I could bring the t over here and put it in the numerator and call that t over 1590, which I can then bring the whole thing up on the natural log of 1/2 to the t over 1590th power. Oh, I'm running out of room. And so as we saw yesterday, we kind of have this ladder that has way too many rungs. Okay, bring that back up. And of course, what is e to the natural log of blob? The blob, and you get the exact same thing. So whether you start with the sect equation or you just start with the pre-cal version, we can call it, either way you can get K. You either build it up or if you want to work with it from the sect equation, you break it down to this one. Okay, so now we can answer the question. How many milligrams of the original sample remain after 100 years? After 100 years. That's going to be what? I'll use this bottom one here. Is 100 equal to T or M of T? T, yeah. So we'll have to make the notation. So M of 100 is what you'd show. And then you'd have 100 times 1/2 raised to the 100 divided by 1590. And of course, if this were a calculator question, that would still, on a free response, be a fine answer. Or if it was a multiple choice question, they would probably be in decimals. So I'm not going to type that in. You can figure it out. What would the units be? Milligrams, yeah, milligrams. How many years, an exact answer, will it take for the sample to have only 3 grams remaining? So what will I do with my 3 grams? Set it equal now to M of T, and I get 100 times 1/2 T to the 1590ths. Now again, I'm using the simplified version of my sect equation. It distills down to something that's much easier to use. If you still kept it in terms of E, you're going to have a lot more baggage going along for the ride. Okay, so now if we solve this for T, what's the first thing we'd have to do? Just reviewing solving an exponential equation. Divide by 100, and that gives us 1/2. And your answers were going to be in terms of natural log. So instead of taking log base 1/2 of both sides, we would take the natural log of both sides. So let me kind of leave a little space there. That's what we'd be left with when we divide by 100. Then we would take the natural log of both sides. And of course, once you take the natural log of both sides, what does that allow you to do with the exponent, bring it out front. So you have t over 1590 times the natural log of a half. All right, so now I need to solve for t. So I need to do two things, and I'll do them both at the same time. I'm dividing by 1590, so I need to multiply both sides by 1590. So it's going to be 1590 times the natural log of 3/100ths. And I'm multiplying by the natural log of a half, so I have to divide through by the natural log of a half. And that should equal t, which I'll put over here on the left. Now that is both a fine and a dandy answer. What would the units be? Years. Okay. Now let's kind of explore other versions of that, because if this were a multiple choice question with no calculator, I doubt that that would be in that form one of the answer choices. So what can we do? In the numerator, because we have the log of a quotient, we can call that what? What can we do with the 3 and the 100? Subtract it, right? We can make it the natural log, not with a highlighter, the natural log of 3 minus the natural log of 100. Now, if you do it like that, you need what around those parentheses, unless you plan on distributing. And on the bottom, there's two things you can do. You could think of the natural log of 1/2, like the numerator, natural log of 1 minus the natural log of 2. And of course, what is the natural log of 1? It's 0, so it's actually gone. So it's equal to the negative natural log of 2. The other way to think about it that way is to say that 1/2 is 2 to the negative first, and you can bring the negative out front and get there a little bit differently. All right, so what might they do? Here's what I can see them doing. I can see them taking this negative factor from the bottom and bringing it to the top. But instead of keeping it out in front of the 15/90ths, I could see them doing what with it? Distributing it. So let's see what that would look like. It would be 1590 times, if I distribute the negative, both the signs would change. It becomes the natural log of 100 minus the natural log of 3 all over the natural log of 2. And then that would be years. That looks like a decent number right there. Relatively pretty, okay? All kinds of things we can play around with logs. I don't think they would mess around with 100, but just to explore, 100 is the same as 10 squared. So you could call that natural log of 10 squared, and in that term you could bring the 2 out front. So that could be 2 natural log of 10. I don't think that would really help. Are there any factors of 100 that divide out with the 3? That would be really one thing we might do, but then of course we'd probably already have simplified it up there. So anyway, there you go, playing around with your answer. And if you want a decimal approximation, right, type it in. Or ask someone who has typed it in. See what they got. Yeah, hopefully not on a test. Thank you. Thank you. Yeah, on AP exams. What'd you get? Now, guys, you're not supposed to be talking. Oh, yeah, that was. Suppose, example 10. Suppose the amount of oil, by the way, that was it. Are there any questions on that? That's more like a pre-cal type problem, right? Because we really didn't do much calculus other than had the option of creating the equation using the differential equation solution, okay? Suppose that the amount of oil pumped from one of the canyon wells in Whittier, California, it decreases at a continuous rate of 10% per year. After how many years will the well's output fall to 1/5 of its present level? Again, more of a pre-cal problem than a calculus problem, but exponential nonetheless. How do we know it's exponential? %, right. Anything that increases or decreases by a constant factor or by a constant percent is also going to be exponential. It has that trademark property of the more you have, the more you get, right? Or the less you have, the less you lose. So after how many years will the well's output fall to 1/5 of its current level? So let's just go to, you want to go to y equals sect or not? Can we create the equation a little bit easier? If we let y be the amount of oil that we currently have pumped by the wells, do we know what the initial amount of oil is? No. What can we do then? Make one up. Very good. And if you're dealing with percentages, Doesn't matter what you make up. What's the easiest number to work with when you're working with percentages? 100. Very good. You'll probably learn that strategy somewhere along the way. Make something up. Let the initial value equal 100 times the base. Okay. If it's decreasing by 10%, what would the base be? Remember, this function is going to tell us how much we have every cycle. If we're losing 10%, we're retaining 9/10. Yeah. So 9/10 as a decimal would be 0.9, or you can leave it as 9/10, whatever suits you. Okay. We're losing 10%, so we're retaining 90%. Or it's 100% minus 10%, whatever. And then you got to convert it to a decimal. And per year. So if we let our t be in years, which is a reasonable thing to do, would we need to make any adjustment to our exponent? No. If it were every 3 years, then we would have t divided by 3. If it were every 6 months and we wanted to use years, then it would be 2t. Very good. T divided by 1/2. Good. Which is 2t. Okay. What do y'all prefer, 0.9 or 9/10? 0.9? Okay, we'll leave it like that then. They're both good. So there you go. In this case, it's a little bit easier to generate the equation if we don't need the k value. This one's easier to use. So after how many years will the well's output fall to 1/5 of its present level? Well, we need to set y equal to 1/5 of what we started with. What's 1/5 of 100? 20, right? 20%. So watch this. If you set y equal to 20, look what's going to happen. You solve for 0.9 to the t, you get 20/100, which is 1/5. Surprise, surprise. And now it's just a matter of solving. You take the natural log of both sides, and you get t natural log of 0.9. Are you okay with me skipping that one step? And then you divide through, and you get t equals the natural log of 0.9. In the bottom, actually. That's a careless mistake I almost made. And then the natural log of 1/5 in the top. So on a free response, there's nothing wrong with that answer. What would we put at the end, though? Time is in years. As a multiple choice answer, do you think that one, like that, would be one of the choices? No, there's a couple things wrong with this. You have mixed combination here. You have, or mixed expressions. You have a fraction and a decimal, both trying to indicate parts of a number. So they would probably stick with one or the other. And on a non-calculator, they would probably go with rational numbers like the fractions. So what's another name for the natural log of 1/5 that wouldn't involve a fraction? Negative natural log of 5. Very similar to what we just saw with the 2. 1/5 is the same as 5 to the negative first, where you get out front, or you get natural log of 1 minus the natural log of 5. So that's a little bit better there. And then, of course, the natural log of 0.9, they might call the natural log of 9/10, which would be the natural log of 9 minus the natural log of 10. Something like that. You think that would be it, though? There's one last thing I see we can do to kind of tidy it up even just a little more. Similar to what we did previously. Take this negative factor from the top, distribute it through to the bottom, and that would have fewer negatives floating around. So now it would be a positive in the top. Both signs would change in the bottom, so it would become the natural log of 10 minus the natural log of 9. Yeah. That's a prettier number. That I can see as an answer choice. So remember, playing around with logs, especially at the end of your answer, manipulating it to get down to something a little bit better. So we know when to stop on a free response, but we also know how to keep going for the multiple choice type questions. And of course, I don't know what the answer is in decimals, so you can type it in. All right, what if we needed to find the value of K? What if it said the amount of oil in the well is proportional to the oil amount in the well changes at a rate proportional to the current amount, according to the equation dy dt equals K times y. What is the value of K? How would we find K? Would we have to reinvent the wheel? Or could we salvage this equation right here? Yeah, we could salvage it, right? Let's repeat what we did yesterday, just in case, all right? If I wanted to make that, which is base 0.9, that's decay. If I wanted to make it into base E, no problem, right? I just use my little property that says E to the natural log of blob is equal to the blob. And so what am I going to have for the blob? 0.9 to the teeth power, right? Just like that. And then if I simplify that, that t can come out front, and I get E t times the natural log of 0.9. And, of course, you can commute those factors. 100 e to the natural log of 0.9 times t. And now you have it in the sect equation, and there is your k. K is the natural log of 0.9. So you have a couple of options. And I got an email the other day from a guy in South Carolina that is using my notes, and he's already on this, and he was asking me if College Board requires you to use the sect equation every time. And what do you think the answer to that is? No. When would you be forced to maybe use the sect equation? When they ask you to find k. Now, if they ask you to find k, they're going to give you that differential description. So, again, you have the option. But exponential growth, exponential decay, very, very important. The more you have, the more you get. The less you have, the less you lose. Okay, here we go. Example 11. I know them by email. They email me. They stumble upon it, I guess. Yeah. I'm missing a negative there. Okay. So suppose that a population of fruit flies, okay, grows in proportion to the number of fruit flies in the population. The more fruit flies you have, the more fruit flies you're going to get. I guess the more fruit you have, the more fruit flies you might get too, right? Exponential, yeah? If there were 100 flies after the second day and 300 flies on the fourth day, how many flies were in the original population? We should have counted them the first time. Could have saved the whole problem, right? When we ordered the fruit flies on the internet and they came in, before we started our fruit fly experiment, we should have counted them. That's good practice anyway, just to make sure that you're getting the right number of flies that you paid for, right? You wouldn't want to be shorted fruit flies. Right. Okay. Oh, well, let's see. We can go to the sect equation if you want. Maybe. You could. Nothing wrong with that. Do we know what C is? C is actually what we're trying to find, isn't it? That's the original amount. If we knew C, we wouldn't have a problem here. We should have counted them. Gosh, dang it. Hindsight 2020. We can sit here and feel sorry for ourselves, or we can move forward and learn from our experience. Let's do that one. Okay. So we need to create some ordered pairs. Let T be the time in days, and let Y be the flies. All right, so what do we know? There were 100 flies on the second day. So at day 2, there were 100 fruit flies. I guess we counted them. On the second day, there were 300 flies on the fourth day. Sorry, on the fourth day, there were 300 flies. Now, with just 2 ordered pairs, you have no idea if that's going to be exponential, polynomial, logarithmic, whatever. But in this case, we do know it's exponential from the description. So I can plug in there if you want. We can do it together. I get 100 equals C e to the 2t. Or I'm sorry, 2k. My bad, 2k. And then I get 300 equals C e to the 4k. And I think I mentioned this the other day. If we don't have the initial condition, we really need to solve that system of equations. And what's the easiest way to do that for exponentials? Substitution could work, right? Divide. Dividing is the easiest way to do it. The method of linear combinations allows you to add, subtract, multiply, or divide any combination, linear combination of one to any linear combination of the other without changing the solution set, okay? So I think I'm going to do, like I did before, 2 divided by 1. If I take equation 2 and divide it by equation 1, here's what we get. 300 divided by 100 is 3. What happens with the C's? They divide out. And we're left with e to the 4k divided by e to the 2k, which is e to the 2k. Very good. Now we can take the natural log of both sides, and we get the natural log of 3 equals what? 2k. and k equals 1/2 natural log of 3. So if they had given us the description and said fruit flies grow down by the seashore. No, that's where she sells the seashore. Fruit flies grow at a rate proportional, and they gave us the dy dt equals k times y, and they asked us to find k, we'd have it. We'd be done. And I don't think it would be as obvious to use the Austin rule. Oops, I gave it away. The Berquist rule. That's what I meant to say. Oh, shoot. But they don't know where you live in New Braunfels. Exactly where on the hill in New Braunfels you live. Huh. In the house with the roof. All right. I forgot what I was going to say. I really forgot what I was going to say. Okay. Oh yeah. Is it obvious then what was happening here? We went from 100 to 300. It tripled, right? It tripled, and it went from the second day to the fourth day. That's in 2 days. So it tripled in 2 days. It holds up. It holds up. Yeah, very good. All right, so now that we have K, we can find C, because we're trying to figure out C. That's our ultimate goal. C is the initial population. So now you can plug that back into either one of those. I like the first one. So 100 equals C e to the 2 times K, which is 1/2 natural log of 3. And now we just simplify. 100 equals C e to the, what's 2 times 1/2 without a calculator? 1. That's why y'all are BC. E to the natural log of 3 is 3. 3 times C is C3. PO, right. Box. What's your PO box? Divide through by 3. Oh, you live in a house. Okay. 100 thirds. 100 thirds? What are the units? Flies. Uh-oh. You originally ordered, or you got in your shipment, I guess I should say at least, 33 1/3 fly. Does that mean there were 33 whole flies and just 1/3 of another fly? Or were there like just a bunch of parts together that made up flies? I don't know. Build your own fly kit. So you had some extra parts. Or maybe you only ordered 30 and you got an extra 3 1/3. So then would you be honest and call the fruit fly people, hey, you sent me too many, I'm gonna ship you some back. You never know, you can ship part of one back. That's right. Right. All right. Okay. Anyway, there you go. Example 12. Here we go. Moving on. What's that? You could leave it as either one of those. I'm not a big fan of mixed numbers. Correct. Yeah. Yep. I mean, you can call it 33.333 if you want to report 3 decimals. That's fine. Exact is always better. Mixed numbers kind of not really. All right. Example 12. This is the last one. This worksheet is not going to be due tomorrow because what's due tomorrow? Test. Okay. So this might give you something to do over the 3-day break. We may make this just due on Tuesday instead of Monday. Example 12. What's that? Does everyone here have a take-home test? Did you get one? Okay, good. 2012, example 5. Relatively recent, right? Relatively speaking. The rate at which a baby bird gains weight is proportional to the difference between its adult weight and its current weight. Oh, okay. Something going on there. At time t equals 0, when the bird is first weighed, its weight is 20 grams. If B of t is the weight of the bird in grams at time t days after it is first weighed, then dB dt equals 1/5 times 100. There should be a minus in there. Don't know why it's missing, but it's acting up. 100 minus B. Now, is that going to be purely exponential growth or decay? Purely exponential growth or decay would be dB dt equals k times b. This is not that. This is some number 1/5 times 100 minus b. So it's not purely going to be exponential growth or decay. It could be modified exponential, though. All right, let's just keep moving. It says, let y equals b of t be the solution to the differential equation with the initial condition b of 0 equals 20. Okay, I'll let that happen. I'll see where this is going. Is the bird gaining weight faster when it weighs 40 or when it weighs 70? Explain your reasoning. Is the bird gaining weight faster? What are we going to do to answer that question? Schroeder, is there an equation that allows us to find how fast the bird's weight is changing? Keep thinking about it. All right? Yeah, it's called dBdt. So, now notice dBdt is only a function of one variable. So you have the option here of saying when b equals 40, okay, you always want to signify that you're plugging something in. And then you can go for it. You could say dBdt equals 1/5 times 100 minus 40. Now remember, on a free response, you don't have to simplify your numeric answer. But ultimately, we need to compare one number to another, do we not? This is called proximity, right, Mr. Cook? They call this proximity in teaching school. All right, so we might want to simplify that. What is 100 minus 40? 60. And 60 divided by 5? 12. Good. Now, what are the units of 12? Grams per what? Time, which is what? Day. Grams per day. All right. So in that case, it was probably better for us to simplify because we needed to compare. Now, instead of saying when b equals 40, because it's a function of a single variable, when we do the second one at 70, you could use Leibniz notation with the evaluation bar. dBdt when b equals 70. That works well, as also well, too. That didn't come out right. 1/5, 100 minus 70, which of course is going to be 1/5 of 30, which is 6 grams per day. Are we done? Do we just box one up and walk away, or do we need to really specifically answer the question? Yes, yes. Now it said to explain your reasoning. Anyone want to take a shot at it? I would say that. I know it sounds silly, but because they said to explain your reasoning, it comes down to elementary comparison of two quantities. Since 12 is greater than 6, comma, yep, the bird gains weight faster when it weighs, what, 40 pounds? Pounds! Dang it. I had it right there and I lost it at the end. Grams. Nice. Big bird. All right, so yeah, there you go. We'll see how much that was worth, where the scoring, where the points came from here in a little bit. We'll look at the scoring guidelines. So far, so good? Actual question. So far, so great. Find d squared b dt squared. What is that? That's the second derivative in terms of b. Easy enough. And then use it to explain. Oh, there's that word again. Dang, my typist is horrible. When the graph of b cannot resemble the following graph. Oh, not when. Explain why. Sorry. Explain. The actual test did not have the typo. This is me transcribing it. Explain why the graph of b cannot resemble the following. This sure looks a whole lot like a what curve that we'll study later again in the year. Logistic. Yeah, this looks like a logistic curve. It says it can't resemble that. We got to see why, and apparently the second derivative is going to offer a clue. Well, first things first. If I have no idea how the second derivative is going to help me answer that question, at least I can find the second derivative, yeah? So let's come down here, and I'm just going to rewrite it. dB dt equals 1/5 100 minus b. Now I'm taking the derivative, so make sure that you use the proper notation. You can do that. d dt colon. It's always good to signal your intentions, as my driver's ed teacher used to say. He was talking about the blinker, not the finger. Okay? But here, you want to make sure that you're always saying when x equals this, d dt colon. Here's what I'm about to do. So the derivative with respect to t of the left side is d squared b over dt squared. We got that. 1/5 can go along for the ride, yeah? It's a constant multiple. So, times the derivative of this. What's the derivative of 100? 0. And the derivative of negative b is negative dB dt. Now, you might get a check for that, I'm guessing, from my experience grading them. But, did we answer the question?
Pardon the interruption, teacher.
No, it said to find the second derivative in terms of what?
You may also watch the
B. And we have it in terms of dB dt. So, let's do one last thing here. d squared b over dt squared. I can pull the negative up front and call it negative 1/5. What is dB dt equal to? Yeah, 1/5 times 100 minus b. Now, is there any obligation on your part to go any further than that? No, not really. But remember, this is also going to offer up some kind of clue as to why the graph can't be the one that gave me. So it might be worth it to go ahead and simplify so that you have something easier to analyze. All right, so let's think about what this means. The second derivative of any function gives us the what of its graph? Concavity. So this function describes the concavity of the graph. And what values of b are we talking about here? T has a domain of, the bird is born, right, weight at 0. So our t has to be positive, yeah? T has to be positive. Well, notice, as long as, I'm sorry, we're talking about b. This is a function of, what is b? b is the what of the bird? The weight of the bird. And it's gaining weight. So t has to be positive, and I guess b has to be positive as well. So if you notice, if b is a positive number but less than 100, then 100 minus a number smaller than 100 is positive, right? And a positive times a negative is going to be a negative. So here's what I know. Based upon the actual second derivative, b is concave down. For what? B less than 100? Yeah? And then similarly, B is concave up. Okay, so this is going to be a positive number. If B is greater than 100, then 100 minus a bigger number is going to be a negative, and a negative times a negative is positive. So B is concave up for B greater than 100. And that makes sense, right? If the bird's weight is less than 100 grams, it's going to be gaining weight at an increasing rate because there's more to gain as it approaches its, ultimate full size. And once it gets beyond 100 grams, it might still be gaining weight, but it can't continue to gain weight at an increasing rate. Otherwise, it becomes the Star of Sesame Street, right? It's going to increase at a decreasing rate. So that's what the equation tells us. Is that what our graph is telling us? Our graph is concave up to around somewhere in here, and now it's concave down for values that are far less than 100, right? So now that we know that the graph should not be concave, what? It has to start off concave down, and it starts concave up. So all you have to do is say something to that effect. How about since, you can add that to there, since above there, B is concave down for B less than 100, B is concave, the given graph is not concave down for all b less than 100. Something to that effect. It already said explain why it can't be. So we said, okay, so since this is what it should be, the given graph is not concave down for all b less than 100. Something to that effect. There are lots of different ways to do it. You just have to make some kind of concavity argument that here's what you gave me, here's what it should be, and at some point they don't match. Okay? Now the last part here, use the separation of variables to actually solve the differential equation with the initial condition. All right, here we go. I'm going to rewrite this. This is where most of the points are going to be coming from, by the way. All that other stuff was just to like make it a little more interesting. Step one is to separate the variables. If I multiply both sides by dt, is that going to be enough to do it? No, I'm going to have to divide through by 100 minus b. Is that enough to do it? I divided both sides by 100 minus b, so I got 1 over that over here, db, and I multiplied both sides by dt, so I left the 1/5 over there. I guess you could bring the 5 over there if you want, but I'm not. Does that do it? That's probably going to be worth a check, I'm guessing. Now we do what to both sides? Integrate, integrate. What's the inside function on the left with respect to b? 100 minus b. This is a real easy thing to do very quickly and miss something very, very important but small. What's the derivative of 100 minus b with respect to b? Negative b. Negative 1. Sorry, negative 1. You speak correctly. Do we have a negative 1 on the top? No, we're off by a negative, so we have to have a negative correction, and that's an easy thing to miss. Now, what's the rule of integration? Natural log of the absolute value of 100 minus b. Do we need a plus c on that side? No. 1/5, the integral with respect to t is just 1/5 t, and then plus c. Now, I'm guessing you get a check on the left, you get a check on the right, and you get a check for the plus c. Just guessing. We can check later. Now I got to solve for b. So what's the first thing I need to do? Multiply both sides by negative 1. So that becomes negative 1/5 t, and negative 1 times c when you distribute is Shamwow c, new and improved c. Absorb the negative. Now I need to unnatural log it by e-ing both sides, exponentiating both sides. We still have the absolute values in place. And now we can do our little trick over here, right? We have e raised to 2 terms in the exponent, that cantilevered c. I'm not going to show the step. You don't have to either. It's going to be e to the negative 1/5 t times e to the c. And what do we call e to the c, the factor now? New and improved c, yes. And if you want, you could just call the exponent negative t/5. It kind of makes it look a little bit better. And with the c in place now in front, what can I do with the absolute values? I can just drop them. If you didn't bring that c in front, you would have to have the plus or minus there still. And now I'm almost there. Just a little shell game. Bring the b over to the right. Bring the c over to the left. And of course, instead of putting equals b over here on the right, I'm going to keep it over here on the left. And there it is. Maybe I'll even make it pretty now, so if that's my final answer, I'll make it a function of t. And there it is. That's the general solution. Is that what we were after? No. It said to find the particular solution. So now we have the initial condition b of 0 times 20. Another error. That should be equals. So let's go ahead and plug it in. So some kind of notation. You could say something like when b of 0 equals 20 or 4b of 0 equals 20. And all we got to do is plug it in. So here we go. We get 20 equals 100 minus c e to the 0 divided by 5 is 0. Guess what? You earn the check right there. As soon as you plug in, you're using the c value. If we solve, we get 20 equals 100 minus c, because e to the 0 is 1. Bring the C across, bring the 20 across, and you get 80. You don't get another point for finding 80, but you do get the point for using the initial condition. So, and then here's your final answer. B of t equals 100 minus 80 e to the negative t-fifths power. And that right there would earn a check. So how many points did I give you for this last piece here? 1 for the separation, 1 for the antiderivative on the left, 1 for the antiderivative on the right, 1 for the plus c, 1 for using the initial condition, and 1 for the particular solution, 6. So that is going to be at least 5, possibly 6, plus maybe, 4 or 3 from the other parts up there. And that was a question in 2012. Had you seen that question like today, how do you think you would have done? Or maybe tomorrow, or maybe by Tuesday after you finish the worksheet? Yeah. Good. Kind of fun. You're dealing with little baby birds and little grams, little tiny little birds, and cute little monkeys. Huh? Little fruit flies, parts of fruit flies. Punky monkey baby. Fruit fly monkey baby. Okay, so take-home test due tomorrow, and we'll make this worksheet due on, I'll say Wednesday. Okay? We'll make it due Wednesday. It's going on next 6 weeks anyway. That way, technically, I didn't give you homework over your 3-day break. Although that would be awesome of me because that would be the gift of math. Yeah. Okay. If you happen to come across any other errors while you're taking the take-home test, just